If you come in early, you can get a seat up here in the front and not have to, stand in the back. So come on down. There's good seats. I don't bite, so. All right, it's my pleasure to introduce Christoph Paulsen, who's going to do the introduction for our third and final plenary session of the morning.
Hey everybody. I have the honor of introducing our next tutorial speaker, Maria Usanova, who was invited here today by the GEM student community during last year's meeting. Maria began her research career at the University of Alberta, Canada, where she started looking at neutron production in lightning strikes using data from the Mir space station. She then switched over to radiation belt physics, where she made great strides in our understanding of particle loss and precipitation due to wave activity using conjugate ground studies as well as space data from FEMS and the Charisma network. She now works at LASP at CU Boulder, is one of the leading experts in electromagnetic ion cyclotron waves, using in-situ data for Van Allen probes to examine direct interactions with the high-energy electron populations. So, Maria.
Thank you for the introduction, Chris. So it's a real pleasure and honor for me to be here in front of you guys. Well, thank you so much for the invitation. As Chris mentioned, I'm kind of like an expert in image waves, so I will probably devote most of my some of slides to MIC waves specifically and how important they are. But the talk today is just a general review talk. I try to put all the information I could find about wave-particle interactions that are important for radiation belts, and including the most recent results, in particular from RBSP and barrel balloon missions. So here's the outline of my talk. I will start with explanation of solar terrestrial environment, single particle motion, adiabatic invariance, wave particle interactions, why they are important for the radiation belts, and I will be talking about the whole zoo of waves that has been observed in the radiation belts, including ULF waves, MIC waves, magnetosonic waves, PLF waves, and all possible sorts of waves there. So, yeah, solar terrestrial environment. Just a very basic concept. So the sun constantly emits radiation, called the solar wind, you all probably know about it. The Earth's magnetic field generally deflects it very well, but periodically energetic particles coming from the sun get trapped by the Earth's magnetic field, get energized, form the radiation belts, which is the this thing. All right, for the radiation belt, mostly I'll be talking about the outer radiation belt that is formed by very energetic order of energy, also called killer electrons, and about the loss processes in this system. So mostly when we are talking about radiation belts, we're talking about magnetic storms, and there are lots of possible effects that geomagnetic storms produce. In particular, there is generation of very intense electric currents and energetic particle fluxes that result in producing aurora borealis and australis. So this is one of the pictures that we took in Edmonton when I was living there. So satellites can cause damage, radiation can cause damage to satellites, space station for polar aircraft flights, can disrupt high-frequency communication, distort radio signals, produce GPS location errors, can also induce unwanted currents in transformer networks, pipelines, etc. So this is a very, very important part of research that has been done recently. And specifically, I'll be talking about magnetic storms and radiation belts and what they do to that the most very energetic particle population. So, as we know, radiation belts were discovered unexpectedly with first satellite missions. So it happened over 50 years ago, but still, even after 50 years, the processes in the radiation belts still remain a mystery. So we don't fully understand them. And in particular, the puzzle is the different response of energetic radiation belt flux to different magnetic storms. So you probably all know this picture as well. So it shows that different storms can produce increases in the radiation belt flux, decrease in radiation belt flux, and little change at all. So it's a very unpredictable system. So the response of radiation belts to geomagnetic storms is determined by a balance between energization and loss, and cannot be predicted so far. However, we do know that wave-particle interactions are important for radiation belts, and hence my talk here. So a little bit of basic stuff as well. So this is periodic charge particle motion. So starting from the fastest motion here is the cyclotron motion. It's the gyration of charged particles around the background magnetic field. So in this case, electrons and ions gyrate in opposite directions. For electron, this gyration happened on the scale of about kilohertz. For ions, it's much slower because of ion mass. So for protons, it will be order of 1 to 10 hertz, depending on the background magnetic field. So the second type of motion is the bounce motion between the conjugate points along the field line. So this happens for 1 eV electrons at geosynchronous orbit on a scale of about 1 hertz. So, and the last type of motion is the drift motion that, again, for radiation belt electrons has a time scale of order of several millihertz. And in this case, we see that ions and electrons, because of charge separation, drift in the opposite direction. And it's important to remember that ions move towards the dusk and electrons move towards dawn. So, invariants associated with this motion are called also first, second, and third adiabatic invariants. One it is that concerned on a time scale that is slower than characteristic periodic motion. So what we're mostly concerned is first adiabatic invariant, also called magnetic moment, second adiabatic invariant related to bounce motion, and the third invariant related to drift motion. Also, just to explain here, so this is a helical particle trajectory, and the pitch angle is the angle between the direction of particle velocity and the background magnetic field. Also important for this talk, because it defines the location of the mirror points, and also as a major thing when we talk about pitch angle particle distributions and the waves that are generated from different sources. So violation of either of the invariants may result in irreversible changes in electron phase space density, also called distribution function. And I'll be talking about the time scales in my second slide, on which time scale on which this violation can happen. So here are the characteristic time scales. They depend on both kinetic energy of the particles and the location in the radiator sphere. So this is the L shell, the distance in the equatorial plane from the center of Earth and Earth radii. And we see here that protons and electrons have different gyro frequency, bounce frequency, and drift frequency. And for protons, for example, with energy of about 10 keV, this characteristic scale would be order of hertz, while for electrons it will be kilohertz. Again, for bounce period, it depends on where in the magnetosphere it happens. It can also happen on a scale of 0.1 hertz for protons, about 3 hertz for electrons. And for drift frequency, it's about comparable. So this is again, I think, pretty useful table that shows all these characteristic scales to remember. So, a very well-known cartoon again, showing locations of different wave modes that can interact with radiation particles. So, what this cartoon showing here is the location of the magnetopause. This is the plasmasphere, a very cold population that is produced by the outflow from the ionosphere. Again, it shows the drift direction of both protons and electrons, so they drift in the opposite directions, and also shows location of different waves that are important. Specifically, location of chorus waves that are high-frequency waves generated on order of electron gyro scale in the dawn magnetosphere. Then AMIC waves, waves generated by gyrating ions on the opposite side, along the dust side, plasma pause, and ULF waves pretty much everywhere along the path of energetic particles. So this is very important because when we characterize the wave, we of course want to know what the wave properties are, what the frequencies are, what are the instabilities that generate these waves, and where, of course, they are located. Because if we want to include all these waves in the big radiation bulk models, we, of course, want to know under which conditions and where they are generated. And in this talk, I will just try to review all the possible wave modes, their main characteristics, what energy particles they interact with, on what scale, and where and under which conditions they are generated. So I will start with the elephant in this system, I would say, because these are the largest waves that are generated pretty much all the time. Of course, they are more intense during disturbed conditions, but this is one of the major contributors to radiation bulk dynamics. So these are the ULF waves, ultra-low frequency waves, also known as geomagnetic pulsations, that cover roughly the frequency range from 1 millihertz to about 1 hertz. So these are the largest wavelengths and lowest frequency in this system. So the amplitudes of these waves are a few nanotesla in magnetic field and a few nanotesla in electric field, but of course the amplitudes vary with geomagnetic conditions. So one of the first classifications of the ULF waves given by Jacobs et al. 1964, and these are the different pulsation classes that we know of today. So they split into two various groups: continuous pulsations that we see quite periodically over a large scale of over long periods, and irregular pulsations, and they also vary in frequency. So for this specific talk, this PC1, PC2 range is important because this is the range where electromagnetic ion cyclotron waves are generated. Also, PC5 waves that are in millihertz range are important because they can resonance with electrons on a drift time scale, and the rest is most important for balanced resonance. I won't be talking much about balanced resonance today. And the regular pulsations are mostly related to substorm physics, so it's all different physics. I won't be talking about it today either. So, okay, so the largest waves in the system. I just like all these pictures, so decided to show them. ULF wave excitation can happen over a very large range of magnetic local times. They can be generated in the subsolar magnetosphere during solar impulses that are coming from the sun. They can be generated in flames due to Kelvin-Hall pulse instability. This is a very instability that is very similar to KH instability that we quite often observe in the atmosphere in form of these clouds. And also they can be generated in the tail of the magnetosphere from different instabilities that result from reconnection, bursty bulk flows, and zero instabilities happening on that side. I won't be talking much about this, but what I will focus on is the effect of these ULF waves, the like BC5 range, on radiation belts. So there are lots of works that has been done here on this topic. I'm not citing all of them, but just the major effects that ULF waves produce on the radiation belts are summarized here. So it's inward radial transfer. So when energetic particles move inwards, they move in the region of more intense magnetic field, and due to conservation of first adiabatic invariant, they gain energy. So the second process is lost due to outward radial diffusion. So oppositely, they can move outward and can meet the magnetopause and open field line, ended up open on open field lines and can escape the system. Then drift resonance that happening on the millihertz time scale lead to more rapid transfer at selected energies. Also, precipitation due to altered pitch angles due to ULF waves can happen in the system as well. So the relevant importance of this is still not very well understood, I would say. And many works related to modulation of ULF waves of high frequency wave growth by ULF waves. And there are many papers that discuss modulation of MIC waves, or force waves, or His waves, and their wave growth on a time scale of BC5 range in millihertz range. So I will, in my talk, I'll just go from low frequencies all the way to high frequencies, not in historic order. So right now I'll be talking about my favorite type of waves that are MIC, also PC1 waves, that technically lie in ULF frequency range. But when we're talking about it in the community, we never call them ULF waves because of these wave properties. So most of we refer to them as MIC waves or PC1-2 waves. So these waves are transverse plasma waves generated by wave-particle interaction and are on a gyroscale of ion, proton, oxygen, and helium. So these main three components, particle species in the magnetosphere, can affect this wave growth. Energy sources provided typically by 10 to 100 keV protons with temperature and isotropy. The typical amplitudes of these waves in space order 1 to 10 nanotesla magnetic field and about 1 millivolt per meter in electric field, so they're pretty intense. They happen in 3 bands, and here I'm showing the spectrogram that shows the local hydrogen, helium, and oxygen gyro frequencies, and these waves can be generated anywhere under these local gyro frequencies. quite often we see them in proton and helium band, sometimes in oxygen band, but in oxygen band there is usually other type of ULF wave activity that is present, so that's why it's really hard to categorize them there. Yeah, 3 bands. Typical frequencies PC1 range from 0.1 to 5 Hertz. And what the importance is that they can precipitate both energetic protons and radiation bound electrons. So this figure just shows where these waves are mostly generated. So this is a geosynchronous orbit. This is the dust side. So most of the waves are generated beyond their geosynchronous orbit in the dust side. So this is standard statistics. These waves are very susceptible to changes following dynamic pressure. This is again the same statistics. So what we show here is that the occurrence is related to changes in dynamic pressure, and for higher following dynamic pressure, occurrence of MIC wave highly increases. Overall day-side sector. The occurrence sometimes also enhances in the EM sphere inside the geosynchronous orbit, though for those ranges of L shells, this is not very pronounced, enhanced. So you really need really high dynamic pressure in order to generate waves in them inside the geosynchronous in the EM sphere. So different statistics from CREST satellite show that the EMIC wave occurrence, and in this case, the authors split EMIC waves in 2 different bands. So the top panels show hydrogen band, and the lower panels show helium band, and they also split it in different levels of geomagnetic activity according to the DST index. So positive DST index quite often associated with magnetospheric compressions. So this is intermediate levels of DST, which is mostly quiet conditions. And the last panel here is DST less than 50 nanotesla, which we assume happening when we have magnetic storm times. So here, what the authors demonstrated, again, there are lots of waves generated on the day side, beyond geosynchronous orbit, and this is mostly seen in the helium and the hydrogen band. In the helium band, the situation is slightly different, so the occurrences are different, and we see that in the inner magnetosphere, there is a significant population that is generated in the dust sector in the inner magnetosphere during disturbed conditions. And this is potentially pretty important for the radiation belts because that's where they overlap with the radiation belts. So for the proton population, situation is slightly different because they are mostly on the day side, and potentially there are 2 different sources for hydrogen and helium population waves. So the helium wave can be due to energetic particle injections during from the tail, while the hydrogen waves might be mostly generated by compressions, but still it's kind of like an open question. So we just need to take into account different processes that may be responsible for this wave generation. So the interesting thing is also when we talk about MIC waves, we can look at their occurrences from different platforms. We can look at in situ data. We can look at ground data. We can also look at polar orbiting satellites. In this case, I'm showing here no satellite. And quite often, when we have a nice conjunction along the same field line, we see these waves both on the ground and in situ. And if we have also a conjunction with polar orbiting satellites, we can look at the precipitating electrons from NOAA. We can look at precipitating ions, and they quite often now started being used as a proxy for MIC waves location if you just look at them simply at the polar satellite data. So what we normally see is enhanced precipitating proton flux in different energy ranges. Sometimes we see it in MOV electron channel that is also sensitive to energetic MOV electrons, but this channel doesn't show the increases in radiation bound electron precipitation often. So the question is when we see this precipitation and why some events do show it and some of the events do not show it is still an open question. So what we did show though that MIC waves do affect radiation belt p-channel distributions. So when we look at different energies, we did a comparison of ground waves for an interval of about 50 days and Van Allen probes wrapped channel data. So we saw that every time we see a wave on the ground, we see a significant decrease in lower p-channel particles on the wrapped. So what it tells us that due to the interaction with MIC waves, these particles were missing from the system. So MIC waves are apparently important for loss of lower energy electron or lower energy p-channel particles. In this case, the range of particles for which this interaction was important confined to pretty much 45-degree angle. But what we do know, and what is important, that these waves do not interact with the core population of radiation belts. So they're not efficient for 90-degree p-channel particles, and for interaction with these particles, you want some other wave modes that can efficiently resonate with them, and then provide further input for MIC waves so that they can interact with that population. So recently, so this is kind of a new results, and I just wanted to point out that there is some wave activity that is very similar to MIC wave activity, but is not MIC waves. So we see it also quite often in Van Allen probe data during enhanced magnetic, disturbed magnetic conditions, quite often during magnetic storms, and they can appear by itself or along with the MIC waves. So these are, in this case, I'm showing oxygen harmonic waves. So these are the spectrogram showing both roughly an interval of 15 minutes on Van Allen probes, two different events, both observed during the storm main phase. And here I'm also showing this harmonics of oxygen gyro frequency starting with the fundamental mode. So they are observed at frequencies about a few to several hertz, same range as MIC waves. They also transverse electromagnetic waves, so they have both electric and magnetic field components. They propagate almost parallel to the background magnetic field, similar to MIC waves, and observed mostly outside the plasma pause. So in this case, plasma pause location is showed here by this magenta curve. So very interesting wave activity, similar to MIC waves. The main difference, if you ask me what is the difference between the MIC waves and this wave activity, that the MIC waves never have this harmonic structure. They often produced in the bands right below the oxygen ion gyro frequency. This harmonic wave tends to sit right on the harmonic on the gyro frequency, even though sometimes we see them shifted. And of course, this harmonic structure, this is what makes them so pronounced. So we also here looked at the wave properties. So this is ellipticity. They do not show typical left-handed polarization that MIC waves quite often show. This is the wave normal angle. Yeah, they propagate less than 20 degrees normally. Energy flux, dominant parallel energy. So the energy, same as wave, normal angle is directed mostly along the background magnetic field. And the Poynting flux can be bidirectional, and in this case, what is shown here is the propagation away from the source region towards the opposite hemispheres, towards the southern and northern hemisphere. So this is quite interesting, I believe, especially since these two examples were observed during the dropout events. I think this is a very good candidate for interaction with radiation belt electrons, though of course we need to do more work on that and study their properties and effect on radiation belts in more detail. So, okay, so I'm going up in frequencies. So the next wave mode is magnetosonic waves. So they also known as equatorial noise. These waves can be sometimes confused with the harmonic waves that I showed before, but their frequencies, they also have this harmonic structure. They can be generated at multiple harmonic of local proton cyclotron frequencies, but their main difference from the waves that I showed before, they are mostly longitudinal electromagnetic waves. So they propagate perpendicular to the background magnetic field, and the main fluctuations in magnetic field are along the background magnetic field. So the frequency range, roughly from 20 to 100 hertz. Amplitudes are smaller, normally smaller than for MIC waves or for ULF waves. So it would be an order of 1 to 50 picatesla. So frequencies are typically between the proton gyro frequencies and all the way up to lower hybrid resonance frequencies. And this is the observation of this type of activity. So don't be confused because this is a logarithmic scale. And it shows the main properties. In this case, the waves were generated close to the magnetic equator. So again, they propagated perpendicular to the background magnetic field. The energy source is believed to be provided by about 10 keV protons with, again, some anisotropy. In this case, it's mostly ring-like distributions, or distributions that have positive gradients and perpendicular velocity distribution. What these waves do, they can accelerate electrons via Landau resonance from order of 100 keV to 1 MeV on a time scale of several days when observed outside the plasma pulse. And this is the typical location of these waves. Most often they are observed outside the plasma pulse. Similar, by the way, to the harmonics wave that I showed you before, also observed outside the plasma pulse. So they can also scatter 90-degree pitch angle electrons due to bounce resonance. And but the efficiency of this process compared to other wave modes may be slightly less. So the relative contribution of these waves and also their effect on radiation belt particles is still questionable. So location of these waves in the magnetosphere is shown here, and similar to the distributions that I showed you before. So I believe this is Van Allen probe statistics covering 3 years of emission. It shows that strongest magnetosonic waves, which are greater than 50 picatesla, and occurrence rate about 20%, happen near the magnetic equator, in the dawn sector, outside the plasma pulse, and of course during discrete conditions. So again, I'm going further up in frequencies. So these are the wave modes that have been discussed for a very long time, and they're probably the first wave modes that were suggested to be important for radiation belt dynamics. So these are Whistler mode waves, Horus and His. So this spectrogram shows observations of this both wave activity on CREST satellite. And what is important to see here, so this is the electron cyclotron frequency. So they observed in the vicinity of electron cyclotron frequency. His waves usually have very broad band structure. They extend from very low frequencies all the way up to high frequencies. Porous waves are structured. They absorb in the vicinity close to the electrocyclotron frequency. The interesting thing is that the spectrum is split by half the electrocyclotron frequency, so there is a gap in wavetivity. But yes, so to identify these waves, we need to look at the spectrum. So this is porous waves. So in the next two slides, I will summarize their major properties. So Whistler mode waves, porous. Again, those are electromagnetic plasma waves. Typical frequencies from 0.1 to 0.8 electrocyclotron frequency with a gap of half the electron gyro frequency that I showed before. So amplitudes are about 10 to 100 picotesla in magnetic field, about 1 to 10 millivolt per meter in electric field, though very large amplitude Whistler waves were also observed. And there were works, for example, by Chris Cali that showed that a very short-living intervals of 0.1 second, where these waves reach huge amplitudes, greater than 100 millivolt per meter, also exist. But recently, I think this is more related to nonlinear interaction and time domain structures that were recently observed on the Van Allen probes, and I will talk about them later. But I just wanted to mention, so yeah, amplitudes can reach pretty high values. So the source for these waves are similar to MIC waves that I was talking about before, but instead of provided by ions, they are provided by electrons with temperature anisotropy T-curve greater than T-parallel, and then the energy range about tens of keV. So these electrons are believed to be injected from the tail of the magnetosphere during disturbed conditions where they gain anisotropy due to the inward motion from the tail to the inner magnetosphere. So they are important for both acceleration and loss processes of energetic electrons, and lower and upper band cores seem to have slightly different properties and be important for slightly different energy populations. So for a lower band cores, interaction with 10 to 100 keV electrons seem to be more important. For upper band cores, they can interact with even like few keV electrons. So the occurrence of cores is according to Wenli statistics from Venice, show radial distance of 5 to 10. So occurrence mostly these waves happen on the dawn side, and they are more intense during disturbed magnetic conditions. So this occurrence is split by AE and X. So we definitely see that more intense waves are observed during disturbed conditions. So Wen also split the observations separately for upper and lower band cores. We see that they show slightly different properties, so maybe even the generation conditions for these waves are slightly different. So next wave mode, Whistler mode His waves. So what is His? So this is mostly incoherent Whistler mode plasma waves observed inside the plasma poles mostly. That's why they're also called plasmaspheric His. These are broadband emissions observed in the range between 100 Hz and 2 kHz roughly, with peak frequency of about 500 Hz. Though some unusual His that can extend all the way down to 20 Hz was recently observed on the Van Allen probes, might be also important and provide slightly different conditions for interaction with the MAV electrons that we thought, or for radiation bubble electrons that we thought before. So the amplitude of these waves are order of 10 to 100 picotesla. They also parallel propagating waves in the generation region. So cores may provide the source for these waves when it propagates through the plasma poles and can evolve into his. So this was one of the suggested mechanisms for its generation, though I think it's still debatable. So some studies indicate that it can be produced by lightnings during thunderstorms. So this is still an open question. Most efficient for lower energy electrons, though can interact with a very broad range of energies. Mainly causes pitch angle scattering and precipitation into the atmosphere for less than 1 MeV electrons on the time scale of days or less, and for more energetic population, the time scales are longer, so the order of 10 to 100 days. So this processes, the fusion processes related to this wave mode are pretty slow. So his distribution. Next slide. So this is Van Allen probe statistics, 2 years of data. Again, the equatorial his amplitudes increase significantly during substormic activity and also show substantial day-dawn side asymmetry. Similar to forest waves, of course, we see the amplitude increase with enhanced AE index, and this statistics is consistent with previous measurements of previous statistics that was done with CRESS data. So, very interesting study that I came across last year and was published in Nature is from Aaron Bregman that shows that his can induce precipitation of 10 to 100 keV electrons on barrel. So I think this is a very neat study. So this diagram shows the location of the satellites, 2 probes A and B, and then the footprints, and the barrel is sitting here. So these are his measurements from the Van Allen probes that were observed for about 2 hours time interval. And the bottom panel shows on the same range X-rays measured on board on barrel. So these X-rays are produced by precipitating electrons when they hit the atmosphere. And the top one shows the intensity of his. And this is a very there is definitely a lot of coherence between the two. So definitely an example of his producing precipitations, which is also modulated by ULF waves that I was talking about in my first slide. So what else is new? So all these activities, all the wave modes that I was talking about before, the MIC waves, magnetosonic waves, coarse waves, quite often, sometimes, not quite often, can show nonlinear structures. So normally, so what these linear structures look like is chirps on top of the background magnetic normal background wave activity. So these chirps indicate there is some nonlinear processes happening, and their importance is also is not very well understood. So there were some measurements showing some particle cell simulations that nonlinear process can cause effective pitch angle scattering and can cause more effective acceleration. They can be also responsible for very short living precipitation interval. But again, I would say it's still work in progress. And specifically, I think it's also a very interesting direction for research to study these nonlinear processes. So next thing that also one of the most recently published papers, broadband electromagnetic waves. We normally don't talk about them in relation to radiation belt dynamics. But what I wanted to focus on is that this broadband activity, and it actually extends from very low frequencies all the way to about kilohertz range, is very often observed during disturbed geomagnetic conditions. So these waves, when I look at the satellite data, I see them very often. I was wondering what these waves are, why they're important, and a recent paper by Chastain et al. Showed that these waves are essentially kinetic alpha waves that are magnetohydrodynamic alpha waves that extend to the range of short kinetic scales. So these scales are the scales comparable to ion gyro radius or electron inertial length, so where kinetic effects become important. So they can cause heating and acceleration for both ions and electrons. This is well known from solar wind observations and simulations. They can interact non-linearly with each other and form power law turbulence spectrum, and they're often correlated with time domain structures that I will address in my next few slides. So I just wanted to point out that they might be important for radiation belts as well, because there is some correlation between their occurrence and occurrence of other structures. So these waves also very typical during storm conditions. So this is statistics again from Chastain that shows that these waves quite often observed in the tail, in the dusk side, and midnight side of the magnetosphere. This probably coming from the tail. No, this is Van Allen probes can only look at the orbits up to 6 Earth radii. But these waves are very important and can propagate all the way to very low L shells and radial distances. So next thing, time domain structures, also called TDS. What are these guys? Well, they're packets of electric field spikes. So what I'm showing here is just a few seconds time series from Van Allen probes observed by David Malaspina. It shows spikes of these very large amplitude waves. Well, in this case, they were about 50 millivolt per meter, but in some very extreme cases, they can reach the amplitude of about 300, which is a huge amplitude. They normally last for only a few hundred milliseconds. They contain a local parallel electric field, very large parallel electric field, and they are assumed to be the mechanism for producing order of 100 keV electrons due to parallel acceleration that can further interact with Whistler waves and can be energized even further up to MeV frequency or energy range. So these things might be also important for radiation belt dynamics, and this is one of their most recent wave modes that was considered a candidate for interaction belt, for radiation belt interaction. So similar to kinetic waves, kinetic alpha waves that I showed before, these waves are quite often observed in the midnight. So this is an occurrence of these waves, and can also propagate pretty well inward into the inner magnetosphere up to about 2 L equals 2. So they're strongest at high L's. They weaken close to the Earth. Concentration, highest concentration at pre-midnight, and they're also pretty symmetric with respect to dawn dusk. So very interesting results. So just to summarize, what I have talked about here before. So radiation belts are affected by the interaction with different wave modes. So I try to review here all the possible wave modes that are important for this. So ULF waves are high amplitude, long lasting, can cause radial transport, energization, and loss. The MIC waves are also pretty strong waves, can cause pitch angle scattering and loss, close to loss cone, most efficient for multi-MeV electrons, don't interact with 90-degree pitch angle particles. Ion harmonic waves, recently observed, may contribute to loss. Chorus waves can produce both acceleration and loss. His waves produce low loss over a large range of energies. Magnetosonic waves can also produce energization, though less efficient than force and gas. Kinetic outflow waves have recently become an interesting topic and may provide seed population for further energization by other wave modes. So time domain structure is also very interesting. Can be also seed population for further energization by forest. Again, large electric fields, but very short-living. So to further, I decided to put all the references here for my talk in the regular paper format. So for further background reading, please feel free to refer to this. So thank you for your attention, and I guess I'll take the questions now.
Thanks, Maria, and we will be posting the talks online, so you don't have to scribble down all of her references here.
Yes, so I just wanted to reference a piece of paper that just got accepted where we look at the typical event parameters and transmission. And one of the things that I have to be careful of is the fact that if you just take the mean of the amplitudes, you get something like 1 nanotesla. If you actually look at the median, the median value for the amplitude is 0.3 nanotesla. And that means that the upper quartile is still below 1 nanotesla. So a lot of these waves are much lower amplitude than we usually do.
Yeah, that's a very interesting observation.
Other questions for Maria? Right.
I noticed you said the magnetosonic waves from 20 hertz to 100 hertz according to the ML paper. I recall that GEOS saw harmonic structure at hydrogen cyclotron spacing in the MSW waves from GEOS, and we also saw from Express, and they went down to half the proton cyclotron frequency, but that wasn't covered. Did they not see that, or was it some different wave, or what?
Well, I guess probably would be the right person to ask that.
Yes.
But I think it also depends on the location where you actually observe these waves and their latitude.
Yeah.
So that might change. I don't know the exact answer to that.
Oh, that's right. It's just another comment. You said the lacquer EMIC waves at less than 4 or something. If you go and look at the Acrobono data, there's a whole zoo of stuff happening at equals 2 to 4 and so on. But that's one of the few satellites that actually traverse that region, so you can get some data useful data.
Yeah. Thank you, Brian.
Please. Yeah.
Observations of magnetosonic waves go down to proton gyro frequency 1 hertz, 2 hertz, and an RBSP. Modules used because they use a search coil which had a lower frequency limit cut off about 20 hertz.
Okay,
That's
yeah,
what
that makes sense.
instruments used to look at them. They go down to the hydrogen gyro frequency.
Yeah, you use the flux gauge. David.
Firstly, great talk, Maria. Covered a lot of ground and did an excellent job. As far as, I'm coming from HIS, of course, as far as the origin of HIS goes, we do know that, of course, it's probably not the only source of wave power that contributes to HIS, but as far as lightning goes, this came up as a really big debate about a decade ago. And, observations did show pretty clearly that lightning does not significantly contribute to HIS. I think the more interesting problem nowadays is figuring out the relationship of these very fast particle injections right into the atmosphere. That seems to contribute sort of some unknown component of HIS, like up low frequencies up through to some reasonable part of the spectrum. So that might be a problem that you're interested in this now.
Thanks for your comment, Jim.
Yeah.
Building on the cost, and that is as we try to deal with wave particle interactions, particularly the waves acting on the radiation belts, we often confront the problem with supported systems that are natural for organizing radiation belt data, particularly the idea of the approach belt, which apply for our wave populations. And I've already asked myself to solve this problem. I wanted to point out a
working on that to make sure we have more comprehensive models that will be easy to use for further improvement in your simulations.
Well, the other that we are looking at the source and the recurrent, I think this is a great system to look at because the recurrent model is a huge program over and this coordinate system. So it depends what problem you want to solve.
Yeah, you've mentioned some of the non-linear aspects of the waves, and I just wanted to point out that it's very difficult to do it in a controlled way in the magnetosphere. But recently, the ECLA group has been working at the LAPD and has generated these chirps of chorus-like waves in the lab. And we can do it in a controlled way so that you can change the plasma parameters and try to understand some of the origin of these very, very interesting waves.
That is fascinating. So how do you control densities in the lab?
Well, you should read there's a paper in PRL and also in GEO. Jacob can tell you more about it since he's more heavily involved.
Okay.
Sounds like a great conversation over lunch. Any other questions for Maria? All right. Well, so if I could get all of the organizers of sessions that are going on this afternoon to come up and do the quick little 2-minute intro of what's going on in your session.